Okay, good morning or hello or whatever's going on. It's actually afternoon right now, 12:01 p.m. on February 11th, 2021. This is Principles of Engineering at Liberty High School. I'm here with Mackenzie and Josh and the rest of my class. What is this, Tuesday, Thursday group? And I want to go over one of the problems from the 1.1.2 Simple Machine Practice Problems assignment. This is a Schoology course page. And so the 1.1.2 Simple Machines Practice Problems, I have made snips of those problems. And I think the one that I want to go over is problem number 9, what I'm calling problem number 9. And problem number 9 is actually in the document number 23, 24, and 25. You can see that here, 23, 24, and 25. And but I just call that problem number 9. Those 3 steps are actually one problem. And so in this problem, you see what it says. I guess I'll read it to you if that's not too condescending. Hydraulic shears are used in manufacturing to cut large sheets of metal. Hydraulic shears are like scissors, sort of. Using hydraulic pressure, the machine pushes a wedge that is shaped as an inclined plane, not biface like an axe. In other words, it's like a knife, but it's only angled on one side. I'll show you the picture that I drew in just a moment. To cut the metal. Imagine one side, there you go. Imagine one side or blade of a pair of scissors. In this problem, a shear has a 1/4 inch thick cutting blade with a 45-degree slope between the 2 sides of the blade. That, to me, when I first read that, was very confusing. So I had to think about it quite a while and then figure out what it looked like, and I'll show you my drawing of that in just a moment. Hydraulic pressure applies a 2,000-pound force to a wedge. It says to sketch it, whatever. It says, what's the length of the slope? Okay. And then what is the ideal mechanical advantage? So after reading that, I look at now my interpretation of that problem, which you will find in the Engineering Notebook Simulator. My interpretation of that problem, let me move this out of the way. I think you can see a little picture of me in this recording. And so in the Engineering Notebook Simulator, that particular problem that I was just doing, where is it? Nope, not there. Okay, almost there. All right, there it is. Let me make that a little bit bigger, maybe a little bit even bigger than that, maybe. Okay, that's pretty good. Now, what I want to do is explain how I took, where was that? Okay, I'm lost. How I took that problem, snips of problems, number 9, I think it is. How I took this problem, the hydraulic shears, cut a metal, imagine one side of a scissor, a shear of 1/4 inch thick, 45-degree slope. So my interpretation of that, after quite a while of looking at it and thinking about it and not being sure, my interpretation of that is this. This is the blade. This is the blade. I can go bigger than I think. Can I go bigger than that and still? Okay, that's pretty good. This is the blade itself. It's at a 45-degree angle, and it's a 1/4 inch. So that I put 0.25 here, 0.25 here, and then there's the 45-degree. And then that little circle, it's like a lasso, little loop. That is the length of the inclined blade, and I just called it L equals question mark. But I'm getting ahead of myself because in the problem, after it gave me the information, 1/4 inch, 45-degree, 2,000 pounds, and that's given, which I put here. The effort force was 2,000 pounds. The thickness is 0.25 inches. And the angle, which I'm using the variable theta, is 45 degrees. So that's given. The picture that I drew is still part of the given. So in the guess process, the 5-step process, G for given, that's the illustration or the sketch I made. And then those given values with those variables. And then it says, what is the length of the slope? I'm calling that L, the length of the slope. And then it also says, what is the ideal mechanical advantage of the wedge? Okay, the IMA, ideal mechanical advantage of the wedge. So I have the given, sketch is part of the given. I have the unknown. And so it looks like the first, and let me see, what did I do here? Did I do this first or this first? I don't know which one I did first. But since L equals question mark is the first one asked for, then I'm going to look at this. And I realized that this is not even necessarily a simple machine problem, or at least the L is not really a simple machine question, but more of a geometry question. What is the length of that blade if it's a 45-degree angle, and if this is a 1/4 inch and this is a 1/4 inch? And what I realized when I was looking at that is, yes, it's geometry. Yes, it's a right angle. which leads us right into the Pythagorean theorem, which everybody learned like in 8th grade. I don't know if you realize it had any application, but this is engineering. In engineering, we apply whatever that stuff is that we learned and didn't realize it had a point. So the length of this is the hypotenuse. If you remember, a squared plus b squared equals c squared, the c in that equation is the hypotenuse of the right triangle, and so that's going to be the L value. And I went ahead and replaced the c squared with L squared. And so this is the given, the unknown, and the equation. And then the substitution, the a and the b, is the 0.25 and the 0.25. So I substitution, 0.25 and 0.25. Remember that those are squared. Those are squared, and even the L is squared, even though we don't know what it is. When you square this and you square this and you add them together, you end up with 0.125. 0.125 is not the answer. It's close, but it's not the answer, because remember that L is also squared. So to figure out what the L is, if the square of the L is this, you do the inverse operation, which is the square root. So you square root 0.125, and my calculator apparently said 0.354. So I wrote down L equals 0.354, and I remembered that the unit that we were using was inches. These 0.25s were inches. Make sure I have the unit. I put 2 lines underneath it to emphasize, hey, that's my answer. Then going back here, well, I got the L. They're also asking for the IMA. Well, I kind of remembered the Pythagorean theorem equation, but I do not know or did not know the IMA equation. So I'm not going to show you right now, but I'm going to trust you to look for yourselves. In the Project Lead the Way website, there is a PowerPoint. And when you view that PowerPoint somewhere among the 30 or 50 or 75 slides, it's not that many, you will find an equation for IMA, which is based on, here it is, the effort distance, d sub E, and the resistance distance, d sub R. I remember that, like I told Josh and Luke just a moment ago. I remember that by thinking it looks like deer, like the animal deer, even though there's only one E, deer, d sub E over d sub R. And this is the ideal mechanical advantage, meaning this is what it was designed. They designed it to be this shape and this size. So that's the ideal mechanical advantage. And if I know the effort distance and the resistance distance, which turns out to be the same distance, this effort and this actually, I think this is the resistance and this is the effort. The distance that the effort, yes, that's it. The distance that the effort is being applied. And then this will be the resistance to that. Well, they turn out to be the same. When you have a number divided by itself, the answer is 1. So the ideal mechanical advantage of this system is 1. When I read this problem, and maybe when you read this problem, I had no idea what they were talking about. And it took me quite a while to translate it into this solution on paper. I hope that was helpful to you. You can hit the like button and subscribe, ring the bell, whatever it is you do. I don't know what any of those things mean. I just have heard people say that before. But I'm going to stop the recording now. And I'm a little bit proud of this one. So bye for now.